Chapter 6 Periodic Table 6.2 Periodicity Part 3, the last part. At the end of this lesson, you should be able to define first ionization energy and explain the variation in first ionization energy across period 2 and 3, as well as down the group 1 to 13 to 18. This will include the irregularity of the first ionization energy between beryllium and boron, as well as nitrogen and oxygen. Generally, the first ionization energy increase across the period and decrease down the group. First ionization energy is the minimum energy needed to remove 1 mole of electron from 1 mole of neutral gaseous atom to form 1 mole of unipositive ion. This is the general chemical reaction for the first ionization energy, where the gaseous atom remove 1 mole of electron to form 1 mole of unipositive ion. In example, if we want to produce 1 mole of potassium gaseous ion, so this is the chemical equation. Factors affecting first ionization energy is atomic size. As we know before, atomic size depends on the effective nuclear charge or ZEF, as well as shielding effect of the elements. Similar to electronegativity, smaller atomic size results to higher first ionization energy. Across the period, variation in first ionization energy across the period depends on the proton number and effective nuclear charge. So across the period from left to the right of the periodic table, proton number increase, thus increasing nuclear charge of the atom, as well as the attraction of nucleus towards the valence electrons. However, the size of atom decrease due to the stronger attraction of nucleus towards the valence electrons. Hence, the amount of energy needed to remove electron from gaseous atom increase, which means it is harder to move that electron due to the size of atom, which is smaller through the right of the periodic table. Therefore, the first ionization energy increase. Small atom needs copious amount of energy to remove its electron. Therefore, the first ionization energy increase. However, there are some anomaly across the period when it comes to first ionization energy. As you can see here, generally the trend of the first ionization energy for the period 2 element increase. However, from beryllium to boron, there is a slight decrease, as well as a slight decrease from nitrogen to oxygen. Let's have a look at the first anomaly in the first ionization energy between beryllium and boron. There is a slight decrease in first ionization energy between beryllium and boron. This is due to the electronic configuration of beryllium, which is 1s2 2s2. Here, as we can see, 2s2 is a fully filled 2s orbital in comparison to boron, which is 1s2 2s2 2p1. And here, boron has partially filled 2p orbital. Only one electron is filled in 2p orbital in comparison to the maximum number of 6 electrons which can be filled into 2p orbital. Fully filled 2s orbital is more stable than partially filled 2p orbital in boron. Therefore, to remove electron from stable fully filled 2s orbital in beryllium needs much higher energy compared to less stable partially filled 2p orbital in boron. Therefore, even the beryllium has bigger size than boron, the first ionization energy of Be is higher than boron. Now let's move on to the second anomaly between nitrogen and oxygen. There is a slight decrease in first ionization energy between nitrogen and oxygen. This is due to the electronic configuration of nitrogen, which is 1s2, 2s2, 2p3. Here, as you can see, there are 3 electrons in the 2p orbital compared to the full 2p orbital with a maximum number of 6 electrons. This is called as half-filled 2p orbital. Whereas for oxygen, the electronic configuration is 1s2, 2s2, 2p4. This is not half, this is partly filled with electron, which is 4 electrons compared to the maximum number of 6 electrons in 2p orbital. Half-filled 2p orbital in nitrogen is more stable than partially filled 2p orbital in oxygen. To remove electron from a stable half-filled 2p orbital needs higher energy compared to less stable partially filled 2p orbital in oxygen. Therefore, first ionization energy of nitrogen is higher than oxygen, or even the size of oxygen, which is smaller than nitrogen. Now, let's have a look at the trend of the first ionization energy down the group. Down the group, the size of atoms increase. This is due to the number of shells filled with electron increase down the group. Since the shell filled with electron increased down the group, the shielding effect increased down the group. The attraction of nucleus towards the valence electrons becomes weaker, therefore the size of atom becomes bigger as we go down the group. Hence, the amount of energy needed to remove electron from the gaseous atom decrease, which means bigger atoms is easier to remove its electron. Hence, the first ionization energy decreased down the group. It means that to remove electron from potassium requires less energy compared to remove electron from hydrogen, which is a smaller atom. Quote of the day: dreams can still come true. You need a great deal of energy and determination, and a little bit of luck. Stefano Gabbana. Before we end our session for today, let's try some exercise. You may pause the video first and try the question yourself before checking the answer. Let's try exercise 1. Now you may check your answer. Thank you.